The universe is often presented to us as a binary system. We see the blazing brilliance of stars, those nuclear engines that light up the void. And we see the rocky or gaseous silence of planets, the leftovers that orbit them. But nature hates a binary. Nature loves a gradient. Between these two familiar archetypes lies a vast, shadowed, and mysterious population of objects that defy simple categorization. These are the brown dwarfs. They are the cosmic middle children, often called failed stars, yet they are the missing links that hold the secrets to star formation and planetary atmospheres alike. For decades they were theoretical ghosts, mathematical inevitabilities that refused to show themselves in our telescopes. Today we know they number in the billions, drifting silently through the dark, possessing storms of molten iron, glowing with a magenta hue, and harboring many solar systems of their own. To understand a brown dwarf, we first have to discard the rigid dichotomy of star versus planet. In the standard model of stellar astronomy, a star is defined by its ability to sustain nuclear fusion. A cloud of gas collapses, heats up, and if it is massive enough, specifically at least 80 times the mass of Jupiter, the pressure and temperature in its core ignite hydrogen into helium. This reaction releases the energy that powers the star for billions of years. A planet, conversely, forms from the leftovers. It accretes from a disk of dust and gas around a star, never gaining enough mass to ignite. But what happens to an object that forms like a star, collapsing directly from a gas cloud, but stops growing at 40 Jupiter masses, or 20? It is too heavy to be a planet, yet too light to be a star. This is the brown dwarf. Astronomers generally define them as objects with masses between 13 and 80 Jupiter masses. Below 13, gravity is too weak to fuse anything, so those are planets. Above 80, gravity is strong enough to fuse hydrogen, making them red dwarf stars. But in that sweet spot between 13 and 80, the core pressure is intense enough to fuse deuterium, a heavy isotope of hydrogen, and in the heavier ones, lithium. This fusion provides a brief spark of stardom before the fuel runs out, and the object begins a slow, eternal fade into darkness. The term failed star is evocative, but perhaps unfair. It implies an intent to become a sun that went awry. In reality, brown dwarfs are successful at being exactly what they are, which are stabilized celestial bodies governed by quantum mechanics. Unlike sun-like stars, which are supported against gravity by thermal pressure, the heat of fusion pushing outward, brown dwarfs are supported by electron degeneracy pressure. As gravity crushes the core, electrons are packed so tightly that the Pauli exclusion principle kicks in. This principle states that no two electrons can occupy the same quantum state. They resist further compression, creating a rigid structure that halts the collapse. This leads to a bizarre physical characteristic, where brown dwarfs are all roughly the same physical size as Jupiter. A brown dwarf with 70 times the mass of Jupiter is only about 10 to 15% larger in diameter than Jupiter itself. It is simply incredibly dense. If you were to add more mass to a brown dwarf, it would not get bigger. It would actually get smaller as the gravity compresses the degenerate core even further. Let us look at the anatomy of these invisible worlds. They form in the same violent nurseries as stars. Deep inside molecular clouds, knots of turbulent gas lose their battle against gravity and collapse. For a true star, the infalling gas continues until the core temperature hits 10 million Kelvin. For a brown dwarf, the cloud fragment is smaller, a runt of the litter. It collapses, heats up, and spins, likely forming an accretion disk, just like a young protostar. This formation mechanism is the primary way astronomers distinguish brown dwarfs from massive planets. Stars and brown dwarfs form via gravitational collapse of a gas cloud, while planets form via core accretion inside a disk around a host. However, this line is blurring. We have found 12 Jupiter mass objects free-floating, likely collapsed clouds, and 25 Jupiter mass objects orbiting stars, likely formed in disks. The universe, it seems, has multiple recipes for making the same cake. The life of a brown dwarf begins with a whimper, not a bang. For the first few million years, they shine relatively brightly in infrared due to the heat of formation. When the core temperature reaches roughly 1 million Kelvin, deuterium fusion ignites. Deuterium is easier to fuse than regular hydrogen because the nucleus already contains a neutron, reducing the electrostatic repulsion between protons. This burning phase acts as a thermostat, keeping the brown dwarf's interior warm and its radius stable, but deuterium is rare. The supply is exhausted quickly, in as little as 10 million years for lighter dwarfs, or up to 100 million years for the massive ones. Once the deuterium is gone, the star goes out. The brown dwarf is now dead. Thermodynamically speaking, it has no new source of energy. It will spend the rest of eternity radiating away its trapped heat, cooling, dimming, and shrinking slightly. One of the cleverest detective tools in astronomy involves lithium. Stars destroy lithium. The convection currents in a young star drag surface lithium down into the hot core, where it is obliterated by protons at roughly 2.5 million Kelvin. Brown dwarfs below 65 Jupiter masses, however, never get hot enough to destroy lithium. Therefore, if you look at a dim red object and see the spectral signature of lithium, you know it must be a brown dwarf. If it were a true star, that lithium would be long gone. This lithium test confirmed the first brown dwarf candidates in the 1990s. Because brown dwarfs cool over time, their appearance changes drastically as they age. Astronomers had to extend the traditional stellar classification system to include 3 new spectral types: L, T, and Y. First, we have the L dwarfs, the red-hot irons. These have temperatures between 1300 and 2000 Kelvin. To the human eye, they would glow a dull, deep red or magenta, similar to a heating element on a stove. Their atmospheres are chemically fascinating. They are hot enough that exotic molecules like metal hydrides exist in gas form. Most notably, L dwarfs are cloudy. But these aren't water clouds. They are clouds of hot dust, tiny grains of enstatite rock and liquid iron. If you could fly a spaceship into an L dwarf, your windshield would be pelted by a rain of molten sand and metal. As the dwarf cools, it crosses a critical threshold into the T dwarfs, the methane worlds. The silicate and iron clouds rain out, disappearing from the upper atmosphere. The sky clears. At these lower temperatures, roughly 700 to 1300 Kelvin, carbon monoxide transforms into methane. Methane is a powerful absorber of red light. This gives T-dwarfs a very distinct spectral fingerprint. In infrared images, they can actually appear blue because the methane absorbs so much of the longer red wavelengths. Finally, we reach the Y dwarfs, the coldest frontier. These are objects colder than 600 Kelvin, with some as cold as room temperature. Discovered only recently, notably by the Y spacecraft, these objects are incredibly faint. Some, like WISE 0855, are frozen worlds with temperatures around -10 degrees Fahrenheit. At this stage, they are indistinguishable from rogue planets. They have water ice clouds, ammonia, and complex atmospheric chemistry. They emit almost zero visible light. They can only be seen by the faint heat signature of their formation billions of years ago. The weather on a brown dwarf makes a Category 5 hurricane on Earth look like a gentle breeze. One of the most dramatic events in the life of a brown dwarf is the LT transition. An L dwarf is blanketed in thick silicate clouds. A T dwarf is clear. How does an object get from one to the other? It doesn't happen gradually, it happens violently. As the dwarf cools to about 1200 Kelvin, the cloud deck begins to fracture. Holes open up in the global cloud layer, allowing heat from the deep interior to blast out. This results in massive variability in brightness, up to 50% changes in a few hours. Imagine a world where half the hemisphere is covered in thick, hot sandy smog, and the other half is clear, exposing the blindingly hot furnace below. As the dwarf rotates, astronomers see it blink. Bright, dim, bright, dim. In the cooler L dwarfs, the atmosphere gets cold enough for gaseous iron to condense. It forms droplets. Gravity on a brown dwarf is intense, often 50 to 100 times stronger than Earth's. This pulls the iron rain down rapidly into the deeper, hotter layers, where it evaporates again, returning to the upper atmosphere via convection. It is a cycle of heavy metal rain driven by winds clocking in at hundreds of miles per hour. Brown dwarfs are also magnetic powerhouses. They spin incredibly fast, often completing a rotation in 2 to 4 hours. This dynamo effect generates magnetic fields thousands of times stronger than Earth's. Recent radio telescope observations have detected auroras on brown dwarfs. Unlike Earth's auroras, which are powered by solar wind, brown dwarf auroras are powered by their own rotation and perhaps the interaction with nearby moons. These auroras are millions of times brighter than the northern lights and emit powerful pulses of radio waves. A brown dwarf might look dark to the eye, but to a radio telescope it is a pulsing lighthouse. The history of their discovery is a story of patience. In the 1960s, astronomer Shiv Kumar theorized that these objects must exist, calling them black dwarfs. For 30 years, they were the holy grail of astronomy. The technology simply wasn't there. Brown dwarfs are dim in visible light and bright in infrared, but infrared detectors were primitive. The dam broke in 1995. TADE-1 was discovered in the Pleiades cluster and passed the lithium test, becoming the first free-floating brown dwarf. Shortly after, Gliese 229b was discovered orbiting a red dwarf star. The smoking gun was methane. Its spectrum showed heavy methane absorption, impossible for a star. It was the first T-dwarf. More recently in 2013, Kevin Luhman discovered a pair of brown dwarfs, only 6.5 light-years away. Named Luhman 16a and 16b, they are the third closest system to the Sun. We have actually made weather maps of Luhman 16b, detecting dark and light patches of clouds rotating in and out of view. Then there is the accident, formerly known as WISE 1534 to 1043. Discovered by a citizen scientist, this object moved fast but looked faint. JWST analysis revealed it is ancient. perhaps 10 to 13 billion years old. It is metal poor, formed before the universe was rich in heavy elements, and challenges our understanding of how cold and old these objects can get. If brown dwarfs form like stars, can they have planets? Yes. And they might be the most common planetary systems in the galaxy. We have observed protoplanetary disks around young brown dwarfs containing enough mass to form Earth-sized planets. In 2004, the first ever direct image of an exoplanet was taken, and it wasn't orbiting a sun-like star, it was orbiting a brown dwarf. That planet, 2M1207b, is a gas giant orbiting a 25 Jupiter-mass brown dwarf. However, there is a theoretical hurdle known as the pebble problem. In a low-mass disk around a brown dwarf, gas drag is strong. Small pebbles should spiral into the dwarf before they can clump into planets. Yet, we see planets. This suggests our theories of planet formation need tweaking. Could life exist here? The brown dwarf itself is likely hostile due to radiation and high gravity. But what about a rocky planet or moon orbiting it? Since brown dwarfs are cool, the habitable zone is very close, often within 1% of the distance from Earth to the Sun. A planet this close would be tidally locked, with one side facing the dwarf forever. The day side would be blasted by infrared heat. The night side would be frozen. Life would be restricted to the twilight zone. The tidal forces from a massive brown dwarf would be immense, likely causing extreme volcanism on the planet, similar to Io around Jupiter. This could keep the planet warm, even as the dwarf cools. When we look for companions around sun-like stars, we find plenty of other stars and plenty of planets. But we rarely find brown dwarfs in close orbits. This scarcity is called the brown dwarf desert. It tells us something profound about formation. Planets form in disks from the bottom up. Stars form from cloud fragmentation, from the top down. The desert suggests that it is very hard for the top-down process to make a small object right next to a big one, and very hard for the bottom-up process to make an object as heavy as 40 Jupiter masses. Because brown dwarfs never burn their hydrogen, they are pristine time capsules. A star changes its chemistry over time through fusion. A brown dwarf retains the chemical composition of the gas cloud from which it formed 10 billion years ago. By studying ancient brown dwarfs, we can sample the chemistry of the early Milky Way. We are entering the golden age of brown dwarf science. The James Webb Space Telescope is perfectly tuned for their infrared signatures, analyzing their atmospheres and finding molecules like silane. The upcoming Nancy Grace Roman Space Telescope will use microlensing to detect thousands of rogue brown dwarfs that are too faint to see directly. And the Rubin Observatory will map the southern sky, catching the flicker of rotating brown dwarfs to help us understand their stormy weather. Brown dwarfs are not failures. They are the bridge. They connect the physics of the very large to the physics of the very small. They challenge our definitions and force us to accept that nature is a continuum. They are worlds of iron rain, diamond dust, and purple skies. They are the silent majority of the galaxy, drifting in the dark, waiting for us to turn our infrared eyes upon them and read the history of the universe written in their cooling embers.